My name is Eric. What's that? Yeah, I'm a technical committee of DSC. So today, DSC and I bring to you guys the ExploreML series workshop. And the topic today is the beginner to machine learning. So this workshop is the collaboration between DSC and ACM education. Okay. So before we go into the core of the workshop today, let's we need to understand what is AI. So artificial intelligence, you probably heard of things about like Alexa or Siri, about how they can recognize your voice. So technically, I mean, in the simplest form, AI is just a piece of software that tries to simulate the human intelligence in the machines so that machines can perform the human intelligent task. Okay, so for examples, is that, let's say the Google Translate software on your phone, right? You can use that one to translate from like English to French. So with that this software, you can like travel to France, and you have no like language barrier. Another more specific application is in the medical industry. Specifically, is the chest disease detection. So here I have a software called ChestNet. So ChestNet is developed by the Stanford University. What does do is that it can detect and classify up to 14 diseases in the chest radiographs, and its performance is really good. Its performance is equivalent to the practicing medical experts. So on your right side here, I have 4 radiographs. So the grayscale radiograph here, they are the input to the ChestNet. And what does the ChestNet do is that it will detect any of kind diseases and classify that. So the output of ChestNet is the yellow-orange mark here. So those yellow-orange mark, they are the location of the diseases that the ChestNet can detect. And by looking at this color radiographs, the radiologists, they can easily and quickly identify the diseases. Okay. Okay, so now you can you briefly understand what is AI. So underneath AI, there are some subfields such as machine learning and deep learning. Both of them, they are software, then they try to simulate the human intelligence. However, the difference between machine and deep learning is that for machine learning is a set of statistical algorithms, and most of the time they work on like tabular data. So the example is that here I have a Excel table. So in this Excel table, I have columns, got date, account, transaction type, and amount. I have the rows. So each row here is a transaction. So as you can see that the machine learning it prefers the input data of table. However, on the other hand, deep learning, what does this do is that it tries to mimic the human brain. So the algorithms behind deep learning is quite different from machine learning, and its preferred data type is the unstructured data set. For example, images, uh, text, and audio. So I mean, one of the simple examples is that, so let's say you develop and train your own deep learning model, then you to classify the dog and a cat. So the input to that model, the deep learning model, is a picture of either a cat or a dog, and then that model will tell you if an animal is a dog or a cat. Yeah. So that's the difference between machine and deep learning. All right, let's move on. So as mentioned in the email, we will provide you two workshops. One is for linear regression and one is logistic regression. So today we focus more on linear regression, and the goal of today is that we try to get you through what is linear regression, the math behind it, and at the end, you can use that model to predict the house price in Boston. Yes, deep learning they can do either supervised learning and unsupervised learning, and also reinforcement learning as well. So that's for today. So tomorrow we focus more on logistic regression that you use to classify things. So the example that we show you tomorrow, which is Sunday, is how to distinguish the Irish, that's Irish flower types. And beside those two algorithms, we also issue two fundamental terms in machine learning. The first one is underfitting and overfitting, and the second one is feature engineering. All right, let's go next. Okay, so that's for the brief introduction to the workshop. So let's code along with me and the DSC. So now you guys should follow this link, the HTTPS trackit.acmutd.co. So track IT is a software developed by ACM members, and it's very cool. And when you get into the track IT, you put in the code linear regression. Okay. Oh.
Once you log in and put in the code, you'll be given the welcome page and you'll be able to code along with us. And then after you click mark as complete, and when we notice that almost all of people have clicked mark as complete, that's when we'll put on the next button, and you all can move on to the next session with us.
Okay, so for track IT, when I log in, right? So here I got login to that track IT, and then I put in the code linear regression. Click go, they should show me this introduction page. And here I have the notebook. So as mentioned in the email, you can either use our own notebook that have all of the codes, or you can create like an empty notebook like this that just have the explanation and don't have a lot of codes here. So with this empty notebook, you can code along with us, as Salani said. Okay. Okay, so I will wait for a couple of minutes so that everyone can get into the track IT and get their notebook set up.
And once you have set up your notebook and you can see the first page, you can go ahead and click on mark as completed.
Okay, so yes, I give me a few seconds. Mm. Okay, so here is the email that you guys will have. I mean, you probably receive it. So here, I'm gonna create a copy, an empty notebook that you can code along with us. So I click on this link. Okay, wait. So with this link here, they so with that link, I will have access to the notebook. And then what I need to do next is that I need to save it to okay. I need to save it to my drive, and let's say to any other drive here. Move here. Okay, so after you save it to the drive, you can open it, or yep. Okay, let me go to my drive. So in my drive, I can open my own notebook. Last modified by me. Okay, so this is the notebook that I just saved into my drive. I just double click on that and click on open in the Google Colab, and that's all you should do. All right, looks like everyone has access to both notebook and the Trackit IT. Okay, Saloni, can you help me go to the next?
Yep.
All right, so as I mentioned that today we focus on linear regression, but I wonder what is regression? Well, we know that linear is a straight line, right? But then what is regression? So theoretically, regression is a program that we try to predict a real value. For example, let's say you work for Google, remotely from Dallas, and then you have a six figures annual salary. So just go out there and try to buy a house in Dallas. And then for every house that you visit, you know a number of rooms and you know the total area, the acres in terms of acres. So based on those information, you try to predict or estimate the price of the house, and the price of the house is real value. So the example is a typical um, regression program. We try to predict the house price based on the number of rooms and the total area of the house. So the solution to that solve the regression problem is using linear regression. Linear regression is one of the solutions here. So linear regression is a machine learning algorithm. It tries to examine the linear relationship between features and labels. Here, what I mean features means that the total area, location, or the number of rooms. These you can use all three of them as features, and the label here will be the house price. Okay. Okay. So
Also, just a reminder that you have to click mark as completed to get access to the next one.
yeah. All right. So here you understand what are features and what are labels. So then here I explained that linear regression it trying to examine the linear relationship between features and labels. So what do I mean linear relationship? What does what means that linear regression, the formula, the math behind it is based on this linear formula, y equal wx plus b. So technically here, x is your input. Let's say your linear regression model takes input, takes x input, the number of rooms and location, and then it would try to predict the y output, which is the price of the house. And W and B here, they are weight and bias. So these two numbers are numbers that the linear regression model try to find in order to make itself predict the house price correctly. So when someone say that they try to train a model, actually they try to find an algorithm that help them to find these two numbers, weight and bias. Okay, so for linear regression, in the simple formula of linear regression, it has it has x as the input variable and depth, and for every x input variable, you have the corresponding weight variable. So when we have more features, let's say here in a simple term, I have only x as location, but in reality, we could have the area feature here. So I will have x area, and then I have another weight for that feature, and then another x variable for number of rooms, and is on corresponding weight. So So in reality, if you have more features or variables, you're just adding more terms of WX for that feature. Does it make sense, Sanjeev? Yep. All right. Looks good. Okay, I move on. So today we will use the linear regression model in order to predict the house price in Boston. So here, the data set that I use to um, train my linear regression model is the Boston house price data set. In this data set, it has 14 features. However, to make this workshop simple, I will just focus on 4 features only. The first one is RM, the number of rooms in the house, the age, which is the year built of the house, right? That is the how accessibility of the house to the highways, and tax is the tax rate. Well, no, to me, I don't like tax a lot. Yeah. So based on those 4 features, I would put those 4 features into my linear regression model, and the target is that I try to predict the house price. So here, MET-V is the mean value of the house price. So I have 4 features, and my target is the MET-V. Okay. Yeah, next slide. Okay, all right. So now, Vincent, he will introduce Pandas, a great data management tool in machine learning. Vincent?
All right. Hi everyone. My name is Vincent. I'm going to be explaining to you guys the Pandas Python package. But first, we need to, if you're starting from a fresh notebook, you need to copy the import dependencies code into your notebook and then run it. And for everyone who's using the template, just run the code for importing your dependencies. Let me share my screen. And then once you've imported your dependencies, we can go ahead and import a data set from sklearn that we talked about before. So that'll be the Boston data set, which is in your tracket. And we use the load Boston function from the Boston data set and set it to this Boston variable. And then when you run that code, this variable should have the data set in it. And then now we need to convert this data set into a pandas data frame using the pd.dataframe function and giving it the data set that we imported before, which is here. And then run that, and then now this variable BOS should have a pandas data frame with the Boston data set. And to output that, we're going to be using pandas.head function to pretty much output the first 5 rows of our data set. As you can see here, all the columns are set to indexes. So we're going to be renaming these columns to give them actual meaning. And to do that, we use dot columns, and then we're going to give it all the names that we want to rename our columns. And then we're also going to output the renamed data frame so that we can see these renamed columns. And then we're going to be adding this new column, which from above was the median value of our Boston data set. And we're getting that from the dot target attribute from our sklearn data set. So let's go ahead and add in our new column and then output our data frame again, and you can see our new column is added. And then we can inspect our columns, see basically what all the column attributes are by using the .info function provided by pandas. And when we run that, it gives us information like the column number, the names of the columns, the amount of entries in each column, if the column can be null or not, and the data type. And then to do some quick analysis using pandas, we can use pandas.describe function, and then it'll give some quick statistics like the count. So this is just the, like from up here, the number of entries in each column, and then the mean, standard deviation, the minimum value, the maximum value, and then some percentage of the value. And then once you complete it, please click mark as complete so that we can move on. So Boston.target is, so the sklearn dataset has two values in it. One is the data value and one is the target value. And the data value is pretty much what we have here, just like the, the initial data, and then the target value is a separate like list of values. It's just one dimensional that it's usually what you want to predict. Oh, Pandas is a Python package used to analyze data sets very intuitively. Dot head will output the top 5 values in your data set, and dot describe is some quick statistics on your data set, or on each column of your data set. And go next. And then now Saloni will be talking to you about data visualization using the Seaborn package.
Saloni, are you talking? We can't hear you if you are.
Sorry, you're muted.
Yep, I'm gonna start again. So C1 is a data visualization library in Python, and it is used to create really pretty data. There are like lots of graphs you can create using Seaborn. We are gonna look at 3 main ones. The first one is a distribution plot, and we are gonna look at the distribution of the variable medv. When you copy paste your code into a Colab, this is what you'll get as an output. As you can see from here, the variables around 15 to 25 have the highest probability of occurring, and most of the variables lie between the range of 5 and 45-ish. The next plot we're going to be looking at is the pair plot. When you pass a range of variables to the pair plot, it's going to print a matrix of plots, which is going to give the plotting of all the relations between the plots. So like you see here, we are giving this 5 variables, and this would show the relation of all those 5 variables. So this would be medv and tax, this would be medv and rad, and so on. Next, we'll be looking at the correlation plot or the heat map. And this is very useful since it's an easy way to find out how strongly or weakly variables are correlated to each other. The first step to doing this is find the correlation matrix. So we give in all the variables we want a correlation of and do .corr to find the correlation between that. And then we pass this matrix to the heat map function, which will generate this really pretty heat map of the correlation between variables. As you can see, the lighter color means strong correlation. So we can see here that there are a lot of variables which have really strong correlation, and there are some which don't have a strong correlation. And when you are done, you can click mark as complete. So over here, we can see the diagonals have a correlation of 1. That is because the diagonals mean that the correlation between the variable medv and medv. And because these values are the same, that means they are really strongly correlated. And that's why they have a correlation of 1. And now Ashwin will talk about scikit-learn.
Hey, let me share my screen. Can everybody see my screen?
Yes.
All right, sounds good. So now we're gonna look at training our linear regression model, and we're gonna do this using scikit-learn. Scikit-learn is just like a machine learning library, which is used for different types of classification and regression. And here we're gonna look at linear regression. And so first, to train the model, we have to select the features that we want to train it with. And as we talked about before, we're going to choose the 4 features: tax, and then age, rooms, and rad. And with that, we're going to use that to predict medv, which is the price of the house. And second. Or no, I did that. Okay. So first, we're going to have to split the data set into training and testing data so that we can train the model on the 80% of the training data, and then we can test the model using the remaining 20%. And for that, we're going to use the scikit-learn model selection library, and we're going to import the train test split library from that. And what that does is basically it splits the data into like 2 sets, which is the X training and Y training, and the X test and the Y test. And so the X train, Y train is like the 80% training, and the X test, Y test is the 20%, which we're going to use to test. And so this can be, the test size is 0.2, 20%. That's what that signifies. And the random state is equal to 10. This could really be any number. All that signifies is that every single time we split the data, it's going to be dividing it based on the same random numbers that it generates, so it can be used to verify the output. And so now we're going to actually go ahead and train our model, and we're going to import linear regression from scikit-learn for that. And this is just the syntax. We're storing that linear regression model into LM. And then lm.fit is just how we train the model, and we're going to train it using the 80%, which is the x.train and the x_train and y_train. And once you run that code, you can see that it works. And so now we've trained our model. And this is just a quick link if you guys want to learn other algorithms from scikit-learn. And now what we can do is we've trained our model on the x-train, y-train, and now we're going to predict it using the same to see how accurate we are with our training. And we're going to predict it using the x-train. And all the predictions, meaning all the y values that we got for the corresponding x's, which is basically a line, we're going to store that into prediction. And after we do that, we can plot it out. So let me explain to you this code line by line. So what PLT is matplotlib. So PLT, a scatter, what it does is it scatters the y train that were the actual values for the x train and the predicted values, which we got through our training model. And it's gonna plot that on this graph. And the plot is from 0 to 50 on the x-axis and the y-axis, and the k just signifies that that the line is a solid line. So, and then the x label is labels, the y labels predictions, and then when you show the graph, you can see that the dots are like the actual values, and the prediction, which is the line, is the predicted values from the x-train data set. In the future, like that is going to go over how this result is changed when we use the actual testing data set, and he will explain that further. And now if you guys could complete, if you click the mark as completed, then you can go on to the next section.
Hello. Wait. All right. Thanks, Vincent, Sari, and Ashwin for explaining Pandas, Seaborn, and scikit-learn. So, okay, wait. Okay, so recently you have seen that we're using, here we initialize an object of linear regression, and then we use fit function to train the model, right? And then we make using predict function to make predictions. So then my question is that what's the intuition behind that? Like how does the linear regression model really work? How it trains itself to become smarter and predict the house price more accurately? So to answer that question, let's I remind you of this linear formula. So within the linear regression model, it is based on this linear formula y equal wx plus b. To make it simple here, I just cancel only one input variable. Let's say it's the number of rooms. Okay, so let's say that I have the x input number of rooms, and then I multiply with its weight and plus with the bias. So this is a formula for linear regression. And y output, which is the price of the house, that is the prediction that the linear regression model tried to make. So x and y, x is the input that we know, and weight and bias are two numbers that the model trying to find out in order to make the model accurately predict the house price. So before we go to the next step to explaining Okay, so right now let's make some math computation here. So first I will define some inputs for the model. So here this array of 4 numbers, 0, 1, 2, 3. So each number is the number of rooms for a house. So here I give the model 4 houses with 4 number of rooms. Okay, so the 0 here, it still makes sense. I mean, not really in reality, but this one is just a demo example. That's an example one. So after I define the inputs, I define weight and bias. So here, as I have only one input variable, I just have only one weight here, and I have one bias. So here I set 0.8 for the weight, I set 0.4 for the bias. Yes, so the weight here is the slope in the math classes. In machining, we call it weight. Okay, so here I have the inputs, weight and bias. Now I substitute those 3 variables into this linear formula. I just copy and paste the code in here into the cell. And here is, and predictions here. And the predictions that the model give me is those for float numbers. And so as a linear, well, the linear regression model, most of the time it won't predict the integer numbers. The range of the predictions of the linear regression model is from -infinity to infinity. This means that the predictions could be A numbers. It could be negative. It could be positive. We don't know exactly. Okay. So do you have any questions for this section? Great. So Mira, so technically in machining, the weight and bias, they are initialized randomly. This means that the 0.8 and 0.4 here, you can pick any numbers. So what happens is that when it training, the model will looking for a better weight and bias. Yes. So the array of predictions here. So let's say 0.4 here is the predicted house price given the 0 rooms. 0.12 is the house price given 1 room in the house. So each number is the predicted house price. All right, let's move on. Okay, so in the first step, the linear regression model, it will initialize weight and bias randomly, and then it will make the random predictions as well. That's how it works. Because initially the machine, the model or the software is, I would say, is stupid. It doesn't know anything. So in order to teach it how well or how bad it performs, we have to compute loss. So here I introduce to you two common loss functions in linear regression. First one is MSE, stands for mean square error. The next one is MAE, mean absolute error. So these are the so this picture here shows you the formula for MS and MAE. Technically here, the E here, it represents for error differences, and then S is where you just square it up, and then mean here, technically you just you compute the average of the square error. Similarly to MAE, means absolute error, the only difference between MSE and MAE is that So here, after you compute the differences, right? In MSE, you square it to make positive, but in MAE, you take the absolute of the differences. Yes, so MSE and MAE, they have the same coefficient 1 over n. So the 1 over n here, it used to compute the average error. Yes, the difference between MSE and MAE is this part only, the square and the absolute. Yes, so actually machine learning and deep learning, they are both based on the same concept of math and statistics. The difference, yeah, but for deep learning, what machine learning, they based on statistics. They are like heavy based on statistics, but deep learning, they have something called like, I would say maybe the human brains that the machine cannot do it. Okay, so in order to show you step by step how to compute the error, so first let's define the labels. So here I have the labels, which is the array of 1 to 4. So each number here represents the house price. Okay, so in order to the next step is that when we compute for MSE, we compute we will perform the calculations from the right to the left. That means that we finish the error, then we go with the square, and we touch the mean. So the first step is that we compute the error here. Error is just simply that you compute the differences between the labels and predictions. You take labels minus predictions, and it is my error. And then after we compute the error, we take the square of the error. Okay, so the square error here, it has basically it just store the square numbers from the error variable. So I have one question for you guys. So do you know why we have to square the error? Yes, Niranj, the error can be more than one. The error, I would say, yeah, it could be any number, to be honest. Yeah, you're right, Pranay. So when we say the errors here, it could be any number, could be from negative infinity to infinity. The reason why we have to square the errors because when we sum up all the errors and compute the average, if we don't square it up, then the negative and positive errors could be added to 0, and it may make the model misunderstand that it performs well, because when the errors is 0, it does mean that there's no mistake, and the model can think may misunderstand that they perform well. So in order to prevent that situation, we have to square the errors. Similarly for MAE, here we take the absolute of the differences in order to make all of the differences or the errors be positive. Okay, yeah. I can show you that. So let's say here, if the labels here, let's say the 2, right? And here my errors will be negative, right? Negative 0.8. And if I don't, okay, that's fine. So if I don't square it up, then I add all those numbers, my errors will be 0.6 plus 1, which is only 0.6, but actually it should be bigger. So here is my, wait, let me run again. So the final step of the MS is that we compute the average of the error. So here I use a mean function, numpy.mean, in order to compute the average of the error. So at the end, I have 0.86 is my error. So in machine learning or deep learning, when someone mentions about loss or error, they always expect or try to make the loss or the error of the model closer to zero as much as possible. Okay, so so far, does anyone have any question? Okay. Oh yeah, sure. So mean square error, it is a function to compute the loss for a linear regression model. Okay, so what does MSE do is that first it computes the differences. So for compute differences, you just simply take the labels minus predictions. And then the S here, it stands for square. So here you see that after I take differences, I square it up. And hence in the computation, we use the square function of numpy to square the error. And I get this square error here. And at the end of the MSE is to compute the average of error, which so in math, you sum all of the errors up and then you divide by n. So in Python, we can simply use mean function of numpy to compute the average of the errors. The error here we computed is very bad because 0.85, I mean, it's not very bad, but like, to be honest, it's bad because we want the error should be very close to zero. Think of like 0.0005 something, not 0.8. That is, to me, that's too big. Yes. Okay. Okay. Okay, so far so good. Okay, let's move on to the next step. Okay, so after we make predictions, and then we use the MSE to teach how well to teach a model how well it performs, and at the end, we go to the step of optimization. So optimization, simply optimization is a method that teaches the model how to update itself. So with the optimization, they're using credit descent. So credit descent is a calculus or a math technique to optimize the weights. So in simply that, in the optimization process, the model will use credit descent to update the weights to make the model make more accurate predictions. Okay. Okay, so in details, what does gradient descent work is that when we use the gradient descent, the model will update the weights for every iteration through the training data set. And the process of updating the weights will be repeated until the loss or the cost, it reaches the global minimum. So here I have an image here showing how the gradient descent work. So initially, let's say here, this is the initial stage of the model when it starts training. So initially, the cost is very high here. So when we apply the gradient descent, the cost of the model will be updated and will minimize until the cost reaches the global minimum here. And when the cost reaches the global minimum, the model stops training. And that's the idea of gradient descent. Oh, cost function is MSE. That's right here. Cost function or loss function, they are interchangeable names, but for a linear regression algorithm, mostly we use MSE or MAE. Here I show you steps to compute MSE. Okay. So let's go. Okay, so gradient descent is a very complex math technique, but simply you can simply think that when we use gradient descent, we update the weight by using this formula. You got a new weight equal to O weight minus D loss. So loss here, this loss is the calculated loss that we compute right here, and then we take the derivative of the loss. So D here represents for the derivative. So in the simplest explanation, D loss, it is just the magnitude of weight change or derivative of the loss with respect to weight or weight. Yeah. So here you take the O weight minus the magnitude of weight change. And if you copy this code into this cell, okay, let me see here. So this is our new weight. So the process of updating the weight will repeat it for every house the model visit. So let's say here we have 4 houses, right? The model will visit. I'm sorry. So the process of updating the weights will happen every time the model goes through the entire data set if we're using gradient descent. Okay. So here we just finished 3 steps in training a model. We making predictions, we compute the loss or the cost, and then we optimize using gradient descent. So those 3 steps, they are combined together in order to train a model. Yeah. So whenever you hear someone saying that they train a model, actually they are doing math right here. Okay. Do you have any questions regarding to optimization in gradient descent? Okay, so if we don't have any questions, we have a fun and quick quiz, Kahoot quiz for you guys. Salani, can you set up the Kahoot quiz? right, it looks like a lot of people share the quiz. Is everyone ready?
So all of the above is the right answer because DSC is most about just us as students learning how we learn certain skills and making sure the mistakes we made others don't make that, and just using those solutions and the softwares we create to help the community. And we do that by participating in the solution challenge.
So Pandas is used for managing data frame, and Skykit is actually used for making training regression models.
Yeah, so ACM stands for the Association for Computing Machinery. We are the largest CS organization at UTD. Our slogan is that we're just a group of people, and our mission is just to give the ECS community the experience and skills necessary to help them get a job in the industry.
So Seaborn is the library used for making data visualization. Scikit-learn, as I said earlier, it's used for training regression models. NumPy is used to manage arrays and other data structures, and Panda is used to manage data frames. So we'll be releasing all this content later. You can always come back to track it and put the code linear regression to get the step-by-step content material. We'll also be putting additional resources in the Discord channel, so make sure you join our Discord. And we also have a GitHub, which we'll link to in the last slide. Thank you for playing along with us, and we hope that you learned a bit more about DSC and ACM.
Thank you. All right. Okay, let's continue. So looks like we have a quiz fun. Well, it's not actually, it's not at the end of a section, to be honest. All right. So I would say that quiz is just, yeah, let's take a break there. Okay, guys, can you see my screen now? Okay. So in the chat, I saw many times you asking about like how good the loss is, how good, how we know the loss is good. So actually, most of the time, the loss I was as good is that when we have a lot of big data set, like let's say 1 million samples, and when the loss is got to 0.8, we can't class that as a good loss. However, for like around 150 samples and we have 0.8, it's not good at all. And because of that, actually, based on that discussion in machining, we have a term overfitting or underfitting. So, okay, let me show you. Wait. Okay, let's remove the plot. So if you copy and paste the code for the area of training predictions section right here into the cell, this here, it will print out the error matrices for the training predictions. So here, the predictions that you make in above, actually it makes predictions based on the training features. And here we compare the training predictions with the training labels. So this code here, it prints out the MAE, MSE, the root mean square error, and the R square error. But now let's focus on these two error matrices that I explained. So based on the training set only, my MAE is 3.8 and my MS is 35.25. As you can see that the error here is very bad. Like it is way higher than 1. That is the error for training predictions. Now, if we make the predictions based on the testing set, what happened next is that so here I use a predict function in a scikit-learn to make predictions to predict the house price based on the testing features, and then I print the loss matrices, I mean the error matrices for test predictions. Okay, then okay, sorry guys. So here it should be white test, not white train. Please fix it. Yeah, so right here, after I make the test predictions, and then I print out the error matrices for testing predictions. As you can see here that my MAE error is 4.4, my MSE error is 41.26, or other numbers. And when you compare this, well, this testing accuracy, actually it's not accuracy. Yeah, sorry. So if you compare this testing accuracy and training accuracy, you can easily see that the error of in the testing predictions is way higher than the training accuracy one. So when you observe the situation that the error in the testing set in the testing phase is higher than the error in the training phase, that is the hint to say that the model got overfitting. So overfitting is a situation that when the model performs well when training, but it performs bad when testing. Okay, this is the definition of overfitting. The reason why, the reason could be that there's not enough data. Like the data is just too small for the model to learn everything. Another reason is that the model is just too simple or too complex. So most of the time, the solution for overfitting is that we simplify the machine learning algorithms or models. Oh, for that one, let's skip the best life fit. Actually, the best life fit, the code for the best life fit, you can look up here, right here, right underneath the making predictions. They are similar. But because when I try to explain about the overfitting and underfitting, if I try to draw out a plot, it may makes you guys confused. So I decided to trap it. So that's what happened to overfitting. Solution for overfitting is that you can simplify the models, or you can try different models. Besides linear regression, you can try like I don't know. There are a lot of algorithms you can try and test it out. We will provide the link to all the algorithms at the end of this workshop. So opposite to overfitting is underfitting. Unlike overfitting, underfitting is the situation that when the model performs bad when training, but it performs well in testing. The reasons, they could be that because the model is just too simple. It doesn't, when the model is too simple, then to fix it, most of the time we try to try or build or invent more complex machine learning models or algorithms. Yes, and in this also another solution is that in this workshop we just focus on only 4 features: radius, text rate, age, and the last one I don't remember. But with the 4 features, if we got underfitting, what we can try is that we can add more feature into the model so that the model has more variables to consider, which is better. And here are 2 solutions for that. So to make it easier to visualize or understanding what is underfitting or overfitting, here I have an image here. So this image for when we got the underfitting situation, so each dot here, it represents for the house. Like not a house, like a data set, or we call data points. And this line here, it represents for the model. So when the model got underfitting, this line here, it doesn't fit to the flow of data points. Okay. And when the model got the overfitting, the line here, the model, it lies right on top of the data points. So in this case, you can easily see that the model just is too fit to the data points. So overfitting and underfitting, these situations the machine engineers or experts, they try to prevent it. And what they expect and we want is that the model just right fit, just the perfect it's a right fit to the data points. As you can see here, the line here just it lies between data points. Uh, it doesn't very far away from data points, or it doesn't like directly on top of the data points. It just goes through in the middle of the data points, and that's and this situation is just the good fit. This is what the engineers expertly want in the machine learning. So the next step is that we introduce to you yeah. So so here are some solutions for overfitting. And overfitting requires to do some like try different machine learning algorithms. But one of the quick fix solution is that we can do fish engineering. So fish engineering is simply that we apply some math formulas to transform, or like I would say to process the data from one format to another one. That's a concept. So one of the future engineering technique is that we normalizing numerical features. So in scikit-learn, the wonderful package, we have a function named min-max scalar. So the min-max scalar function, what it does is to convert, let's say we apply the min-max scalar on the age feature, right? Then all of the age samples, it will be converted to a zero. It will be converted into a fixed range numbers. And by default, the min-max scalar, it will convert all of the ages to the range of 0 and 1. Standard scalar, it does similar thing to min-max scalar, except that standard scalar, it using statistics such as standard deviation to normalizing numbers. However, to make it simple, here we're just using min-max scalar. So here, all the codes for the feature engineering, they are provided, so you don't need to copy and paste the code. So here I import the min-max scalar function from scikit-learn, and then here I make a copy of the dataset to the boss.df variable. The next step is that here I apply the min-max scalar function on text radius from the house to the highways, the age of the house, number of rooms in the house, and then so here I take all those features and I put into the min-max scalar function so that it can compute the range of the numbers, and then I apply using min-max scalar with the transfer function to convert all of the numerical numbers of those 4 features into the same range, and with the process numbers I pass back to the boss.df data frame. And then if you inspect the age here column here, you can see that our age here right now, the mean of the age is 0 and the max of the age is 1. Yes. So after we normalizing the numerical features of data set, we repeat the process of selecting features. Then we split the data set into 2 sets, training and testing sets. And then I initialize another linear regression model, and I train it model with a fit function given the X train and Y train. And then the next step is that we're making predictions. So here I also throw out the plot that's showing the matches between the predictions and labels. So the solid line here, it represents for the perfect matches. So the more dots here close to the perfect line, the perfect matches line, then the better the model performs. The next step is that we need to check the errors, because the idea of applying the feature engineering is that we try to solve the underfitting and overfitting. In other terms, it means that we try to apply the feature engineering to boost the accuracy or the performance of the model. So here I got the accuracy of the model with normalizing features, and here is my loss. And then here I also copy and paste the accuracy of training of the model. Here is the loss of the model without the normalizing features. And as you can see, easily see that the errors of both, they are exactly the same one. What I can say is that here sometimes the feature engineering may help us to boost the accuracy, sometimes it not. So in this case, it doesn't help us to boost the accuracy, which does mean that it requires us to try and test all the machine algorithms. And then after we make predictions based on the training features, and make the predictions based on the testing features. Okay, so there should be a text. It should be fine. There should be a text here. So here is my accuracy. Well, this is the loss that I got from the tested predictions, and this is the loss that I get from testing predictions without normalizing features. So if we compare these two, again, I don't see any big difference between the loss. As I explained in the past, the feature engineering, it may help us or may not. So in this case, it doesn't help us to boost accuracy. So we have to try all the machine algorithms. Yep, and that is all of the that's the end of the workshop today. So do you have any question regarding to feature engineering or other things? Okay, if not, then that's the end of workshop. I'm gonna start presenting. So if you still have questions, you can put the question into the channel named Explore Beginner ML. Thank you.